Unit 3, CheMystery. You can access this video and this review at srhschem.wikispaces.com and on YouTube channel Leffellabs. The first problem is asking us about methane and water, and it's going to ask us some questions about the VSEPR shape, so we need to make sure we have our VSEPR chart out. So first we need to draw Lewis dot structures for each compound. We have methane, which consists of carbon and 4 hydrogens. Carbon has 4 valence electrons, and it needs 4 more to get to an octet, which is a stable configuration. So carbon can form 4 bonds. Hydrogen has 1 valence electron, but for hydrogen, a stable electron configuration means 2 valence electrons. So it only needs 1 more electrons, so hydrogen can make 1 bond. But there are 4 hydrogens in this formula. So first we have to determine our central atom. Our central atom is going to be the one that can form the most bonds, and it will never be hydrogen. So that means carbon is our central atom. I have to attach to that carbon 4 hydrogens. And we know that each hydrogen is going to make a single bond, which means 2 electrons. So one of those 2 electrons will come from the hydrogen, and then the other one will come from the carbon. So if we count the number of electrons, there's 8 total around carbon, and each hydrogen has 2, so all of these atoms have achieved a stable configuration. My central atom is carbon. And there are 4 bonding pairs, that's 4 bonding groups on the central atom. And there's no lone pairs on the central atom. So if we use our VSEPR chart, then we see that the shape for this particular molecule is going to be tetrahedral. We're going to go through the same procedure for water. Water has 2 hydrogens and 1 oxygen. Oxygen has 6 valence electrons. In order to get to a stable electron configuration of 8, it needs to gain 2 more electrons, meaning that oxygen can form 2 bonds. Hydrogen can only form 1 bond because it only needs 1 electron in order to have a stable configuration. So we'll start with our central atom. So that's going to be the one that can form the most bonds, but it will never be hydrogen. So oxygen will be my central atom, and I have to attach to that 2 hydrogen atoms. So those hydrogen atoms can form single bonds. We can go ahead and place the electrons for oxygen. So there's 1, 2, 3, 4, 5, and 6 are going to be paired up, leaving those 2 unpaired electrons free to form a bond with hydrogen. Once again, if we count, we get an octet for oxygen and 2 electrons for each hydrogen, which is stable configurations all around. My central atom was oxygen. Attached to the oxygen were 2 bonding pairs, so that was 2 of those bonds with the hydrogen atoms. And I also have 2 lone pairs. So these are the electrons that are not forming a bond on the oxygen. So based on this information, we use our VSEPR chart and we see that the shape for water is bent. Next question asks us to use that VSEPR shape to predict the polarity of each compound. So we determined that methane was tetrahedral. So the carbon to hydrogen bond is actually slightly polar. So those electrons are actually being pulled towards the carbon. But this molecule is highly symmetrical because of the tetrahedral shape. So what that means is that those bond dipoles are going to cancel each other out. So these electrons are being pulled in opposite directions, which cancels out that polarity. So overall, the methane molecule is going to be nonpolar, even though it has polar bonds. With water, that oxygen to hydrogen bond, each of those is very polar. The shape is bent. So what that means is that those dipoles do not cancel out. So what we end up with are regions of charge. The dipole is pulling the electrons towards the oxygen, giving a greater oxygen electron density than we have around the hydrogen. So we get those two poles. Thus, water is polar. Next, we want to use intermolecular forces to explain which substance is going to be more likely to be a gas at room temperature and which one will have a higher boiling point. So the main intermolecular forces, we have dispersion, dipole-dipole, and hydrogen bonding. So intermolecular forces are the attractive forces between molecules. It's sort of like how sticky those molecules are for one another. So dispersion forces are very short-lived, temporary dipoles. This occurs in all covalent molecules just due to shifting electron clouds. Dipole-dipole interaction occur in polar covalent molecules, and hydrogen bonding occurs in covalent molecules that have a hydrogen attached to an F, O, or N. Basically, all of these are just attractions that occur between molecules within a substance. So in dipole-dipole, we have the polar part of one molecule attracting to another molecule. And in hydrogen bonding, that's a lot like dipole-dipole, but the dipole is so strong that we give it a special name and we call it hydrogen bonding. So if we look at methane, methane is definitely a covalent molecule. But we just determined in the last slide that it was nonpolar, so we're not going to have dipole-dipole. Additionally, we don't have a hydrogen attached to an F, O, or N, so we're not going to have any hydrogen bonding in methane either. Water is also a covalent molecule because it's all nonmetal. It is polar. We just described that in the last slide. So it has dipole-dipole. And those hydrogens are each attached to an oxygen, meaning that we also have hydrogen bonding. So methane is going to have very weak intermolecular attractive forces, and water will have really strong attractive forces. So for this reason, methane is going to be a gas at room temperature. So those intermolecular forces are pretty weak and it's not being held together very tightly. So those particles are going to be able to spread really far away from each other. It's going to be very diffuse. It's going to be a gas. Boiling point is a measure of how much heat do I have to put in something before those attractions break apart and it turns into a gas. So for methane, those attractive forces are very weak, and for water, they're very strong. So I have to put a lot more heat to boil water than I have to put into methane. So water has those really strong intermolecular forces that hold it together. So it's going to take a lot of heat to disrupt that attraction and allow those molecules to separate into a gas. Next, we've got a pair of molecules, and we want to predict which will be a higher boiling point. So methane is going to have dispersion because it is covalent. If we look at the other molecule, this is methanol. And in methanol, we're going to have dispersion because it's all nonmetals. It is covalent. This molecule is actually also polar. If we were to draw a line, we would see that it was unsymmetrical. And we have a hydrogen attached to an oxygen, meaning that it has hydrogen bonding. So methanol is going to be much more attracted to itself than methane is attracted to itself. So I'd have to put more heat into boiling methanol. And in fact, at room temperature, methane is a gas, but methanol is a liquid. If we look at our next two molecules, we have to treat them the same. So first we have some H2O. This is a covalent molecule, so it has dispersion. It's a polar molecule, so it also has dipole-dipole, and those hydrogens are attached to oxygens. So we've also got hydrogen bonding. In the case of H2S, this does also have dispersion because it is covalent, and it is also polar, giving it dipole-dipole, but it doesn't have hydrogen attached to F, O, or N. those hydrogens are attached to sulfur, so it doesn't have hydrogen bonding. So in this case, the one with the higher boiling point is going to be water because it's got more intermolecular forces. It takes more heat to disrupt those forces and allow it to turn into a gas, to allow it to boil. Next question is to use VSEPR theory to explain why carbon dioxide contains polar bonds, but this molecule is nonpolar. So if we look at the electronegativity values for carbon and oxygen, the difference there is a difference of 1.0. So if we look at our electronegativity differences, a difference of 1.0 is going to be either moderately polar covalent or very polar covalent. So that carbon to oxygen bond is definitely polar, but the molecule is nonpolar. So if we look at the VSEPR shape for carbon dioxide, the shape is linear. So what that means is that the bond dipoles are pulling those electrons in opposite directions. So on one end, it's being pulled towards one oxygen, but on the other end of this linear molecule, it's being pulled in the opposite direction. So because those electrons are being pulled equally in those two opposite directions, those dipoles are going to cancel out. So this molecule is nonpolar, even though it contains polar bonds. In order for us to know that, we have to look at the shape of the molecule. Hexane is nonpolar while water is polar. So explain in terms of intermolecular forces why they cannot form a solution. So here I have a solute and here I have a solvent. So to form a solution, the solute and the solvent must be able to interact with each other. And those interactions must be stronger than any of those interactions for themselves. So in other words, the solute and solvent must be more attracted to each other than the solvent is attracted to itself and the solute is attracted to itself. So charged, which include polar and ionic substances, they can only interact with other charged substances. So if I dissolve a solute in a solvent, we're going to form all these interactions between solute and solvent. Those interactions are only possible because the solute and solvent have similar polarities. Hexane is nonpolar, therefore it cannot interact with polar water. So those intermolecular forces are not strong enough in order to form a solution. So what happens is the solvent is more attracted to itself and the solute is more attracted to itself than they are to each other. So there are going to be no interactions. The solute only interacts with itself and the solvent only interacts with itself. Therefore, they cannot form a solution. The next question, we have some balancing for some equations and then determining the type of reaction. So the first step, we can draw a line, and then we're going to make a list of all of the elements and ions that we have on each side of the arrow. So first we come across lead, and then the next thing that we have is actually a polyatomic ion. We have hydroxide. So if you have that polyatomic ion present on both sides of the arrow, you can just count the polyatomic ion as opposed to breaking it up into its individual elements. So instead of breaking it into oxygen and hydrogen, we can just count the number of hydroxides. It makes it a little easier to balance. So right now, it looks like we don't have hydroxide on the other side of the arrow, but that's because it's hiding in water. I can rewrite water instead of H2O. I can write it as HOH. So whenever I write it that way, it's pretty obvious that I've got a hydroxide and a hydrogen. So my hydroxide, my hydrogen, and my chlorine. So now I'm just going to take inventory. I've got one lead, two hydroxides, one hydrogen, and one chloride. On the other side, one lead, one hydroxide, one hydrogen. Be careful that you don't count the hydroxide twice. You don't want to say that there's two hydrogens whenever we're counting one of those hydrogens as part of hydroxide. And then we have 2 chlorides. So we can see that this equation is unbalanced. So I'm going to go ahead and start with the hydroxide. So if I put a 2 in front of the HOH in front of the water, that's going to give me 2 hydroxides, but it's also going to change the number of hydrogen to 2 as well. So it looks like we've taken one step forward and one step back, but this is actually really good because now I can go to the other side and put a 2 in front of the hydrochloric acid, and that'll give me 2 hydrogens and 2 chlorides. So now my equation is balanced. If you look at this equation, the lead is switching places with the hydrogen. So instead of Pb hydroxide, it becomes hydrogen hydroxide. And we switch places, we get lead chloride instead of HCl. My next one, I've got nitrogen and hydrogen. So on my reactant side, I've got 2 nitrogen and 2 hydrogen. On my product side, I'm making ammonia. I've got 1 nitrogen and 3 hydrogens. So this looks like it is going to be a little tough to solve because we've got a 2 and a 3. But what we should do is we should try to think about what my common denominator is there. So the common denominator between 2 and 3 is going to be 6. So I'm going to aim to get 6 hydrogens on each side. I also know that I have to put a 2 in front of the NH3 so I get 2 nitrogens on my product side. So that leaves me with 2 nitrogens and 6 hydrogens. So on the other side, I can go ahead in front of the hydrogen and put a 3, and that'll give me 6 hydrogens on both sides. So now that my equation is balanced, this is a combination reaction where 2 reactants become 1 product. And my next one, I have sodium, chlorine, and fluorine. I've got 1 sodium, 1 chlorine, and 2 fluorine on my reactant side, 1 sodium, 2 chlorine, and 1 fluorine on my product side. So I'm going to start by putting a 2 in front of the sodium fluoride. So what that will do is it'll give me 2 fluorides, but it also changes my sodium. So then I can go back onto my reactant side and put a 2 in front of the sodium chloride, and that gives me 2 and 2 sodium and chloride. So now my equation is balanced, and this is going to be a single replacement. You can see that the fluorine is kicking out the chlorine. So that's one element being replaced. The fluorine is a lone element. It kicks out the chloride, and that becomes chlorine as a lone element. So this is a single replacement. So next we have KClO3, and that's going to give me potassium chloride and oxygen. So I start with my potassium. ClO3 is a polyatomic ion, but it doesn't appear on both sides of the arrow. So I'm going to have to break that up into chlorine and oxygen. I've got 1 potassium, 1 chlorine, 3 oxygen atoms. On the other side, I've got 1 each of potassium and chlorine and 2 oxygens. So once again, we're faced with a situation where we don't have 1 on the side that is in balance. We've got 3 and 2. So for those 2 numbers, we got to think about what the least common denominator is, and that's going to be 6. So we're going to aim to have 6 oxygens on both sides. That's our goal. So in order to do that, if I put a 2 in front of the potassium chlorate, that's going to give me 6 oxygens, but it also gives me 2 potassium and 2 chlorates. On the other side, if I put a 3 in front of the oxygen, that's going to give me my 6 oxygens, but in order to fix the KCl, I have to add a 2 in front of that. So that's going to give me a balanced equation. This is a decomposition reaction because I start with 1 reactant that breaks down into 2 products. The next one, we have methane, CH4, reacting with oxygen. So I've got 1 carbon, 4 hydrogens, and 2 oxygens on my reactant side. And then on my product side, 1 carbon, 2 hydrogens, and be careful, 3 oxygens. I have oxygen in 2 places, with the carbon dioxide as well as with the water. So I want to make sure every time I change something that I count both of those. So to me, the easy place to start is going to be with hydrogen. If I put a 2 in front of H2O, that's going to give me 4 hydrogen on my product side. And I've also changed the number of oxygen. So I have 2 oxygens with the carbon dioxide, and that 2 is distributive in front of water, so that gives me 2 more oxygens for a total of 4. So at this point, I just need to put a 2 in front of my oxygen to get 4 total, and now this equation is balanced. This is a combustion reaction, and we know that because we have a hydrocarbon reacting with oxygen. My products are carbon dioxide and water. Next, we have some reactions, and we want to predict if they will occur or not. So for single replacement reactions, these will only happen if the lone element is more reactive than its counterpart in the compound. So my lone element is sodium. Sodium is a cation, which means that it can only replace another cation. So the other cation is magnesium. So we have to ask ourselves, is sodium more reactive than magnesium? So if we look on the activity series for metals, sodium is higher up than magnesium, meaning that it is more reactive. So this is a reaction that would actually occur. So what I need to do, I'm going to basically switch partners. So instead of sodium being by itself, now sodium is going to be with chloride. This is an ionic compound, so we should check our charges. +1 and -1, that works out. And then now magnesium is going to be by itself. In this case, we're talking about just solid plain magnesium. It's not in a compound, so we don't have to worry about its charge. So at this point, my formulas are correct, but my equation is not balanced. So if I look on both sides, I've got 1 sodium and then another sodium, so 1 on each side. For magnesium, I've got 1 on each side, but I've got 2 chlorine on my reactant and only 1 on the product. So to solve this, I have to put a 2 in front of the sodium chloride. So that's going to give me 2 chlorines on each side, but now I have 2 sodiums on my product and only 1 sodium on my reactant. So I can resolve that by putting a 2 in front of the sodium. Next, the lone element is going to be bromine. So anions like bromine can only replace other anions. So in this case, my anion is chlorine. So will bromine replace chlorine? Only if bromine is more reactive. And if we look at the activity series for halogens, we see that bromine is actually less reactive, which means that this reaction's not going to occur. For the next set, once again, same rule applies. For single replacement reactions, they're only going to happen if that lone element is more reactive than the element in the compound. So I've got copper as my lone element, and cations like copper only replace other cations. So my other cation is hydrogen. So is copper more reactive than hydrogen? If you look, copper is under hydrogen, which means no, there's going to be no reaction here. Let's look at the next one. My lone element this time is fluorine. Fluorine becomes an anion in compounds, and anions can only replace other anions. So the fluorine is going to replace the chlorine so long as fluorine is more reactive than chlorine. So we can see that fluorine is more reactive than chlorine. Therefore, this reaction will happen. So what I need to do is switch spots, switch potassium so that it's with fluorine instead of with chlorine. So I'm going to have potassium and fluorine. Potassium has a +1 charge. Fluorine has -1 charge, so that works out. And then by itself is going to be the chlorine. Now, chlorine is one of my diatomics. So if you have elemental chlorine, that's chlorine just by itself, it's not going to be Cl, it's going to be diatomic Cl2. So now we have our correct formulas, but our equation isn't balanced. So I've got 1 potassium on each side of the arrow. Then I've got 1 chlorine on the reactant side and 2 on the product side. I've got 2 fluorine on my reactant side, but only 1 on the product side. So I'm going to start by putting a 2 in front of Kf. That gives me 2 fluorides, but it also gives me 2 potassiums. So if I go over to the potassium chloride and put a 2 there, that gives me 2 potassiums on each side, and it also gives me 2 chlorines on each side. For each of the following, write balance and determine the type of reaction. So we're starting with potassium metal. So that's just going to be K, potassium all by itself. And that's going to react with chlorine gas. Don't forget, that's one of the diatomics. So it's Cl2. That's going to combine together to form potassium chloride solid. So the charge on potassium is +1, the charge on chloride is -1. So those charges work out. We can go ahead and put in our state symbols. So potassium metal will be a solid, chlorine gas, and solid potassium chloride. We've got our equation written properly. We just need to go ahead and balance it. So I've got 1 potassium and 2 chlorines on my reactant side and 1 each on my product side. So to fix this, I'm going to start by putting that 2 in front of potassium chloride. That gives me 2 chlorides, but it also gives me 2 potassiums. So then my solution is to go to the other side and put a 2 in front of the potassium. And now my equation is balanced. This is a combination reaction because 2 things combine to make 1 product. Solid copper and aqueous sulfuric acid. So sulfuric acid is an ic acid, which means that sulfur was originally sulfate. So sulfate is SO4. This is an acid, so I'm going to put a hydrogen in front. Hydrogen has a charge of +1, and sulfate has a charge of -2. So in order for this formula to work, I need 2 hydrogens. Those guys react together to give me aqueous copper 2 sulfate. So copper 2 means copper with a +2 charge. We already established that sulfate was SO4 with a -2 charge, so this ionic compound works out +2 and -2. I'm also going to get water, which is H2O, and sulfur dioxide gas. So there's nothing in front of the sulfur, which means 1 sulfur, and dioxide means 2 oxygens. So I can use the prompts in the word equation to fill in my state symbols. Solid copper, aqueous sulfuric acid, aqueous copper 2 sulfate, liquid water, and sulfur dioxide gas. So now I'm going to want to go ahead and balance this. So start with my copper. After that, I've got hydrogen. The next thing that I have is sulfate. So I do have sulfate on both sides, but sulfur appears in more than one place. So I'm just going to treat them separately and look at sulfur and oxygen as if they were separate elements. So 1 copper, 2 hydrogens, 1 sulfur, 4 oxygens. On the other side, I've got 1 copper, 2 hydrogens, 2 sulfurs. Careful, it's in 2 places. And 7 oxygens. So oxygen is actually in 3 places. There's 4 from the sulfate, 1 in the water, and 2 in the sulfur dioxide. So that's a total of 7. So I'm going to start with the easy one, which to me looks like sulfur. So if I put a 2 in front of H2SO4, that's going to give me my 2 sulfurs on each side, but we've changed the number of hydrogen to 4, and we changed the number of oxygen to 8. So it looks like I haven't quite fixed this yet, but if we take a look at the hydrogen, If I put a 2 in front of the water, that's going to give me 4 hydrogens total, but it also changed the number of oxygen. So I have 4 from the sulfate, 2 from water, and 2 from the SO2, which will give me a total of 8. This reaction is actually a single replacement reaction. It doesn't exactly look like one, but if you look, you see that the copper replaces the hydrogen. We make some other stuff as a byproduct, but the copper is replacing the hydrogen. So this is going to be a single replacement reaction. Sodium phosphate solution. So sodium is Na with a +1 charge. Phosphate is a polyatomic ion, PO4, with a -3 charge. So in order for this ionic formula to work, I'm going to need 3 sodiums. I'm going to react with calcium chloride. Calcium has a +2 charge and chloride has a -1 charge. So I need 2 chlorides for my charges to balance out. I'm going to form sodium chloride, +1 and -1, so those charges work. And I'm also going to form a calcium phosphate precipitate. So calcium would have a charge of +2, phosphate has a charge of -3. So in order to make this work, if I have 3 calciums, that gives me +6, and if I have 2 phosphates, that gives me -6. So those are my formulas. The sodium phosphate is a solution. The calcium chloride is a solution. I'm going to form sodium chloride solution and calcium phosphate precipitate, which means solid. So now that I've got my equation properly written, I can go about balancing it. So I've got sodium on both sides. I've got phosphate on both sides, calcium and chloride. So on my reactant side, 3 sodiums, 1 phosphate, 1 calcium, 2 chlorides. On my product side, I have 1 sodium, 2 phosphates, 3 calciums, and 1 chloride. So I'm going to start with my phosphate. So if I put a 2 in front of the sodium phosphate, that's going to go ahead and give me my 2 phosphates, but it also gives me 6 sodiums. Now I'm going to go ahead and fix my sodium. So if I put a 6 in front of NaCl, that gives me 6 sodiums, but also 6 chlorides. So in order to fix everything up, I need to get 3 calcium and 3 chlorides on my reactant side. So if I put a 3 in front of that, that gives me my 6 and my 3, and now everything's balanced. This is a double replacement reaction where the sodium and the calcium are going to switch spots. And this reaction will definitely occur because one of my products is solid. For the next set of questions, we're going to be predicting the products of double replacement reactions. And we need to use our solubility guidelines because we need to determine if the reaction occurs, and if it does, we have to write out our net ionic equation. So I'm starting with sodium nitrate, which is aqueous, and calcium hydroxide, also aqueous. So first thing I need to do whenever I'm predicting these products is determine the charges on all of my ions. So sodium is +1, nitrate is -1, calcium is +2, hydroxide is -1. So in a double replacement reaction, the cations are going to switch partners. So we're basically just going to swap ions. So sodium is going to switch spots with calcium. So instead of sodium nitrate, I'm going to get sodium hydroxide. Charge on sodium is +1, hydroxide is -1. Those charges work out. Now I'm going to have calcium with my nitrate. Calcium is +2, nitrate is -1. So in order for this to work, I need 2 nitrates. So at this point, I've predicted what my products are going to be. Now I need to go ahead and use those solubility guidelines to determine if they're going to be aqueous or solid. So sodium hydroxide, sodium is a group 1 ion, and group 1 ions are always soluble. So sodium hydroxide is going to be aqueous. Next, I've got calcium nitrate, and nitrates are also always soluble with no exceptions. So if I was going to write out my net ionic equation, we can go ahead and we can balance this. So I've got 2 hydroxide on my reactant side and only 1 on the product side. So if I put a 2, that gives me the 2 hydroxides on both sides. It also changes the number of sodium to 2. I also have 2 nitrates on the product side. So to resolve this, if I put a 2 in front of the sodium nitrate, that gives me 2 sodiums and 2 nitrates on each side. So to write out my net ionic equation, I'm going to go ahead and write out the individual ions. I have 2 sodium ions, 2 nitrate ions, 1 calcium ion, and 2 hydroxide ions. So the formula has OH2, meaning 2 hydroxide ions. For my products, I've got my 2 sodium plus 1 ions, my 2 hydroxide ions, my calcium ion, and my 2 nitrate ions. So to write my net ionic equation, I'm going to go and start canceling out things that appear unchanged on both sides of the arrows. So calcium plus 2 aqueous cancels calcium plus 2 aqueous. If it's the same on both sides, it's going to cancel out. So what we've encountered now is that everything is canceled out. And that's because there's no reaction. All of these ions just float around together in the water. There's no formation of a solid driving this reaction. So all those ions just float around. We get no reaction. For my next one, I've got lithium hydroxide solution and copper sulfate solution. So I want to figure out my charges. Lithium is +1, hydroxide is -1. The charge on sulfate is -2, which means that the charge on copper has to be +2. So the lithium and the copper are going to switch places. So instead of copper being with sulfate, now it's going to be with hydroxide. The copper was +2, hydroxide was -1, therefore I need 2 hydroxides. That leaves lithium and sulfate. Lithium is +1 and sulfate is -2, so I'm going to need 2 lithiums to make this formula work. Copper hydroxide, if we look at our solubility rules, we see that hydroxides are usually insoluble, and there's a couple of exceptions like group 1 and ammonium, but copper is neither of those exceptions. Therefore, copper hydroxide is going to be a solid. So this reaction happens. For my lithium sulfate, lithium is a group 1 ion, and those are always soluble with no exceptions. So that will be aqueous. We can go ahead and balance this. So I'm going to start by putting a 2 in front of my lithium hydroxide. That gives me 2 hydroxides on each side of the formula, as well as 2 lithiums on each side of the formula. I already have 1 copper and 1 sulfate on each side, so now I'm balanced. So I'm going to write out all of my ions. I need 2 lithium ions, 2 hydroxide ions, a copper ion, and a sulfate ion. And those are going to form my solid. We don't separate that one into ions because it's not aqueous. And then I've got my aqueous lithium ions, 2 of them, and my sulfate ion. So I'm going to do as I did before and cancel out things that appear the same on both sides of the arrow. So lithium cancels out, it's aqueous on both sides, and the sulfate cancels out, it's aqueous on both sides. Nothing else will cancel out. So my net ionic equation is going to be 2 hydroxide ions plus a copper +2 ion to make copper hydroxide solid. Use symmetry to determine if the following are polar or nonpolar. So basically what we want to do is just cut these in half and see if they're the same on both sides. So with water, if I cut it in half this way, it's asymmetric, which means that it will be polar. In the case of the chlorine, no matter how I cut it in half, it's still highly symmetric. So chlorine is going to be nonpolar. My last one is kind of a trick. I've got charges, which means that this is ionic. It's not polar or nonpolar. It's ionic instead. I've got a metal and a nonmetal. Next question. Some of the following compounds are incorrect, so find them and figure out and explain why they're not correct. So my first one, I've got CaH2, and we're calling that calcium hydroxide. So first, that's not right because hydroxide is OH minus 1. So if I wanted to have calcium hydroxide, I would need CaOH2 in order to have the right formula there. Otherwise, I could call this calcium hydride. FeSO4, we're calling that iron sulfate, but iron is one of those transition metals where we don't know the charge. Therefore, I need a Roman numeral in this name. So to figure out the charge of iron, well, I can look up the charge of sulfate. That's -2. And there's only one iron, so the charge on that one iron has to be +2. So to fix this, I would call it iron 2 sulfate. Next, I have H2SO3, and we're calling that sulfuric acid. So this is an ic acid. It's blank ic acid. So that sulfur originally ended with 8. Sulfate is SO4. We have SO3, so that's not correct. So if I want the right formula, sulfate has a -2 charge. We put in hydrogen in front since this is an acid. And I'm going to need 2 hydrogens for this formula to work. So now we are correct. Next, I've got CrNO3 and we're calling that chromium 2 nitrate. So the charge on nitrate is -1, and there's 2 of them. Therefore, the charge on chromium must be +2. So this works out. Next, I've got potassium 2 cyanide, KCN. The problem with this one is that we know that the charge of potassium is always +1. It's not a transition metal. Therefore, I don't need that Roman numeral. So I should just call this potassium cyanide. Last one, we have nitrogen trioxide, N2O3. This doesn't work because the formula has 2 nitrogens and the name has only 1 nitrogen. So I'm missing that prefix. So this should be dinitrogen trioxide.